Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video, the last of this section, we're going to talk about Descartes' Rule of Signs. René Descartes, a famous French philosopher, mathematician, whose big saying was, "I think, therefore I am," also gave us the XY coordinate plane, probably more important than that, and we're going to talk about the rule of signs. So this is a way of figuring out what types of solutions and a function, what type of zeros a function may have. So if we have a function f of x that's a polynomial function and all the coefficients are real and the constant term is not zero, that's important. We can figure out how many positive real zeros there are by looking at the changes in sign from term to term in f of x. And they have to be in descending order, right? Descending degree. Then, if we look at the changes for f of negative x, that will help us to figure out the ones for negative solutions. So for part A, the changes in sign, the number of those variations, there can be at most that many positive zeros. If there are less than that, it will be by some even number less than that. So say we find that there could be 9 positive zeros. There could also be 7, 5, 3, or 1, right? Keep going down by 2. If we take a look at f of negative x and we count the variations of sign, that gives us the maximum number of negative solutions that we could see. And then, again, it could be less by some even number. So if there were 4 possible negative solutions, it's either going to be 4 or 2 or 0. Right? Keep going down in steps of 2. So we're going to take a look at a couple of examples, and we're going to revisit one problem from an earlier video to see how that worked. Determine the possible numbers of positive, negative, and non-real complex zeros of this function. Negative 3x to the fourth plus 15x cubed minus 50x plus 17. So we're going to count the variations in sign of these coefficients. And yeah, I'm going to start with this. So the first coefficient is negative to positive. That's one variation. Then we go from positive back to negative. That's a second variation. And from negative to positive, now we've got 3. So the number of positive solutions, or positive zeros, the max it could be is 3. 2 less than that is 1. So 1 is also a possibility. 2 less than that's negative 1, and that can't happen. So there's either going to be 3 positive zeros, real, or 1 positive zero. Now we look at f of negative x. And that's negative 3 times negative x to the fourth power plus 15 times negative x to the third power minus 50 times negative x plus 17. Negative x to the fourth power, when we raise a negative quantity to an even power, it becomes positive. So this first term is really the same as negative 3x to the fourth. So its coefficient is negative. Negative x to the third, when we raise it to an odd power, that result is negative. So we have 15 times negative x cubed, or minus 15x cubed. Negative 50 times negative x is positive, so that's plus 50x and plus 17. And there's only one change in sign. Negative to negative is not a change, but negative to positive is a change. There's 1. So for negative zeros, there can only be 1. So let's try to summarize what we've got in this problem. Positive, negative, and the rest have to be non-real complex. And remember, those always are going to show up in pairs because if a complex number is a solution, so is its conjugate. The first possibility is that there are 3 positive zeros, 1 negative zero, and since this is of degree 4, the maximum solutions are 4. So 3 plus 1 is already 4. That means that in that case there would be 0 complex solutions. If there was only 1 positive, we know that there can only be 1 negative zero, and that would leave 2 non-real complex solutions. How would you go after solving, finding these zeros? Well, I say that because we know there's 1 negative solution, find that. Then look for one of the positive zeros. That takes care of 2 of them, and that knocks this 4th degree polynomial down to a 2nd degree polynomial. And then you can figure out whether you have 2 more positive solutions that are real, or are there 2 non-real solutions. You could use quadratic formula to figure it out at that point. Let's try one more. Problem 9. Determine the possible numbers of zeros of each type for this function. F of x equals x to the 4th minus 18x cubed plus 25x squared minus 35x plus 14. There's one change. There's another, and another, and another. That's 4 variations in sign. So for positive zeros, there could be as many as 4. Now knock that down by 2. There could be 2. Knock that down by 2. There could be 0. Knock that down by 2. We're into the negative numbers, and that's, you can have a negative number of solutions. So the positive solutions are either going to be 0, 2, or 4. Let's take a look at the negative ones. And again, we want to look at f of negative x. Negative x to the 4th power, remember, is still x to the 4th, minus 18 times negative x cubed. We've got a negative as a factor 3 times, multiplied by another negative 18. That's going to be positive, so plus 18x cubed. And that's not a variation in sign. Plus 25 times negative x to the 2nd power. Negative x raised to the 2nd power is positive x squared. So that term's coefficient is going to stay positive. Still no variations. Minus 35 times negative x, that's plus 35x. And plus 14 we just bring down. There are no changes in sign. Every one of these is positives. Every one of these is positive. So negative zeros, we know there are none. So what are the possibilities? Positive, negative, non-real, complex. Well, there could be 4 positive and 0 negative. There could be 2 positive and 0 negative, or 0 positive and 0 negative. Because the degree was 4 for this polynomial function, the total number of solutions, including multiplicity, has to be 4. So in the first case, there would be 0. In the second case, with 2 positive, that means that there would have to be 2 that were non-real. And if there are 0 positive, that means that all 4 would have to be non-real. So it's one of these 3 scenarios. You go looking for the first positive root. If you find one, you know there has to be another one. So working with only the positive zeros first. After you found 2, now you're down to a quadratic situation again. And that means that you can use quadratic formula to find the last 2, whether they're going to be positive or non-real. I wanted to go back to an example from the last video that I did, because we had a function we were trying to find the zeros of, and we saw that there were 2 that were real, one was positive and one was negative, and we had two that were complex. So let's see how Descartes' rule of signs could have showed us that that was a possibility. Looking at the f of x, I'll just do it in blue. There is one variation there, positive to negative. Negative to positive, that's a second one. Positive to negative, that's a third one. So for positive, it was either going to be 3 or 2 less than that, which is 1. For negative, using the idea that the even degree terms, where the exponent is even, those are not going to change, but the terms with an odd degree, an odd exponent, are going to change. F of negative x would have been 2x to the fourth plus 15x cubed, that one changes, plus 18x squared, same as it was, minus 90x, that one changes, minus 200. And we only see one variation in sign, from the positive 18 to the negative 90. So for negative, the only option was 1. So the scenarios, let's go positive, negative, and then non-real. One option would have been 3 positive with 1 negative, leaving 0 non-real. Or 1 positive with 1 negative, leaving us with 2 that were non-real. And that was indeed the case here. We had one positive solution for 1 negative 0, negative 5 halves, and 2 non-real there. If I didn't know that 3 plus I was a solution, the first thing that I would look for is the negative 0, because we knew that there was going to be one of those. Then I would look for the positive 0 that I knew was guaranteed to be there. There had to be at least one of those. And then at that point, I would have been left with a quadratic function that I could have found the other zeros using the quadratic formula. All right, so that's Descartes' rule of signs. Take a look at the variations in sign of the function for those coefficients. Take a look at f of negative x, count up those variations of signs, and those will give you the possibilities for positive zeros and negative zeros. The rest have to be non-real complex, and they always happen in pairs. All right, that's the end of this section. I will see you in the next one.